65 million years ago, a very important and catastrophic event changed the course of life on land. And although we know that the land animals I'm going to talk about are just the scum of the earth that on the land, the little bits of land floating around, but they are important to us because they're sort of in our scale of experience from millimeters to meters. And these animals disappeared, and a separate life, mammals radiated out to take their place. And so we know this in extraordinary detail. So this is a core from near Bermuda. We know that the tsunamis, the earthquakes, and the things that we've experienced in the entire record of humankind history can't really quite get around the kind of disaster that this represented for the Earth. So even before that impact was known, even before scientists in general came to an agreement over the theory of evolution, scientists and natural historians of all kinds of stripes actually had divided Earth's life's history into these two episodes: Mesozoic, the middle life, and the Cenozoic, the recent life. And as it turns out, it actually corresponds really nicely with geologic history. So we have a Mesozoic period, an age of fragmentation, and a Cenozoic period, an age of reconnection, South America to North America, India to Asia. And so my work really is trying to understand the character of that Mesozoic radiation compared to the Cenozoic radiation, see what mysteries we can understand from dinosaurs and from other animals about what life on drifting continents really can tell us about evolution. The work immediately begs the question, oh, why didn't they go into the waters? I mean, certainly mammals did. This is one example. You can go outside, you see many other examples. Within 5–10 million years of the bolide impact, we had a whole variety of animals going into the water. Why didn't they do that? Why didn't they hang around in trees at good size? And why didn't they burrow? Why didn't they do all these things? And if they didn't do all these things, what kinds of animals were in those spaces? And if there were no animals in those spaces, what does that tell us about, how evolution works on land? Really interesting questions. I think a lot of it has to do with body size. In fact, I think most of it has to do with body size. The size you are when you inherit a vacant ecospace for whatever natural disaster. Looking at dinosaur evolution, studying it, digging it up for many years, I end up looking at the mammal radiation, and it seems as though everything is quick time, just like technology advancing by an order of magnitude. Dinosaur evolution proceeded at a stately pace, an order of magnitude slower on any way you want to measure it. You want to measure it by diversity. You want to measure it by the time it took to reach maximum body size. Yes, they do have larger body size, but many of them are smaller. But we're interested in the time it took them to achieve that, 50 million years to achieve this maximum body size. And that is 10 times longer than it took the mammals to achieve maximum body size and invade all those habitats. So there's lessons to learn, and there's lessons to learn from the exception that we know very well today from discoveries we've made and many other scholars have made around the world. This slide was shown before. This is the famous Jurassic bird, Archaeopteryx. We now know this transition is the one time that dinosaurs actually went below that body size. We're going to see where they began in a minute. And it is the one time that they rapidly invaded all the habitats I just told you that dinosaurs weren't in. They became marine. We now know them today from the ice caps. There's burrowing birds. They inhabit the trees at all body sizes, and of course they inhabit the land. So we were the first to actually name a bird from the famous series that later exploded onto the pages of Science and Nature. We called this bird Cynornis. It's a little bit more advanced than Archaeopteryx, and if you go to different layers, you find things that are less advanced than Archaeopteryx and every grade in between. So that if you find something today, we're usually splitting hairs, or more appropriately feathers, as to decide whether it's actually a non-avian or an avian. It is the greatest transition that we have actually on land from one habitat to another, there bar none, to understand how a bony, fairly heavy kilogram or a couple of kilogram animal could make such a transition. It is really one of our greatest evolutionary sequences. Now, my work began at the beginning. I thought if I'm going to understand dinosaur evolution, I'd have to go back to those beds where they had picked up fragments, go back to a time and a place where the earliest dinosaurs existed. I'd like to call for this little video clip to give you some idea of sort of what we face normally. We get asked a lot of questions. Well, how do you find fossils in areas that look like this? If we could roll that first video clip. This is sort of a nice helicopter ride through those early beds, and they're located in northeastern Argentina. And we're coming over a cliff, and at the top of that cliff, dinosaurs have basically taken over. at the bottom of the cliff, we find that they're rare as hen's teeth. That's where dinosaur origins is to be found, at the bottom of the cliff. You go into an area like this, you've got a geologic map, you've got a topographic map, and the best, most inspired team you can bring to the area. And the rest is up to you. You've got to find fossils, you've got to dig a hole that's usually quite a bit bigger than that to get it out. You've got to climb those cliffs and find, really, everything that exists there, not just the dinosaurs, but the entire story. If you're lucky, you dig a place like that, you actually find the ash bed to date it, and we did. 228 million years old. We found what really is the most primitive dinosaur. That's the dinosaur. A 3.5-foot thing, beautiful skull, predator, meat eater, a two-legged animal. So all the other dinosaurs that you know, or your kids know at least, in 4 legs. This is sort of a look at the skull, and it's absolutely fantastic thing, about 5 or 6 inches long. It's rather bird-like, because it is. It's bird-like and hollow, a predator, maybe 25 pounds or 10 kilograms. That's where dinosaurs began. That's where the radiation began. That is 10 times larger than the mammal radiation, which was a 4-legged radiation. We are extremely dinosaur-like and unusual in our 2-legged approach to life. Now, if you want to understand what happened then when the continents broke apart and dinosaurs found, landlubbers as they are, found themselves adrift, there's some missing puzzle pieces. Most of those missing puzzle pieces are southern continents, because it was those continents that are least explored. If you want to add to this picture and try and sketch it globally, you really have to force yourself to go down to the 4 corners of the earth, Africa, India, Antarctica, Australia, and start putting together some of these pieces. And I'm going to consider, I've been to some of those continents, but Africa was, in the words of Steven Pinker, was a blank slate, largely. But one with an immense chalkboard in the middle, with lots of little areas of dinosaur rock, if you could survive an expedition. There's no roads into the Sahara, it's an enormous place. To be able to excavate the 80 tons of dinosaurs that we have in the Sahara and take them out, you really have to put together an expedition team that can handle the conditions. Some of them are political, many of them are physical, some of them, the most important, are mental. And you really have to be able to withstand conditions. You have to drive into the desert. You will see landscapes. In many cases, you can see from what we discovered that nobody else has ever seen. And the kinds of teams they bring in, well, they're composed of people who understand science as adventure with a purpose. They're usually students who've never seen a desert. Some of them are more experienced. Your job as a leader, this is definitely a team sport. Your job as a leader is to try to inspire them to do more work than they've ever done in their life under conditions that they can't imagine. So 125 degrees is normal. The ground surface at 150, typical. So you can't leave your normal metal tools out, because you'll get a first-degree burn if you grab them sometimes. So you are finding yourself also in an amazing cultural milieu. You're really rubbing shoulders with the world's last great nomadic people. These are the Tuareg nomads that are living their lives much as they have for centuries. Your job is to excavate things like this in the foreground and make them enter the pages of history. To do that, you've got to actually transport them thousands of miles out of the desert. We talk about Ethiopia, let's talk about Niger, or Niger in our English language, north of Nigeria. That's where this photograph was taken. Basically, you're talking about a country that, when we started working there, did not have container traffic. You transported the bones out yourself to the coast of Africa onto a boat if you wanted to get them out of the middle of the Sahara. That's a 2,000-mile journey. So enormous excavations and a lot of work, and out of essentially a partial herd of dinosaurs that you saw buried there, 20 tons of material, we erect Jobaria, a sauropod dinosaur, like we haven't seen on some other continents. It really is a little bit out of place temporally. It looks nothing like what we would find if we dug in contemporary beds in North America. Here's the animal that was causing it trouble. And, you know, on and on, a whole menagerie. When you pick up something like this, and some of you have had the chance to touch it, this is a piece of history. You're touching something that's 110 million years old. This is a thumb claw. There it was moments after it was discovered. It is an incredible view of life, and it really began when we began to understand the depth of time. It's only been with us for less than a century, and that time, that fourth dimension, when radioactive dating came about less than a century ago, and we could actually tell how old some of these things were, is probably the most profound transformation, because it changes the way we look at ourselves and the world dramatically. And you pick up a piece of history like that, I think it can transform kids that are possibly interested in science. That's the animal that thumb claw came from, Suchomimus. Here's some others. This is something we found in Morocco, an immense animal. We prototyped by CAT scanning the brain out of this animal. It turns out to have a forebrain, 1/15 the size of a human. This was the cover of Science because they thought that humans were more intelligent than these animals, but we can see by some in our administration that despite the enormous advantage in brain volume, some of the attitudes remain the same. Anyway, smaller raptors, all the stuff from Jurassic Park that you know of, all those small animals, they all come from northern continents. This is the first skeleton from a southern continent, and guess what? You start preparing it. It has no big claw on its hind foot. It doesn't look like a velociraptor. It's really a wholly separate radiation. So what we're trying to piece together here is a story. It involves flying reptiles like this pterosaur that we reconstructed from Africa, crocodiles, of course, and that's a nasty one we haven't named yet, and huge things. I mean, this is a lower jaw just laying there in the desert of this enormous crocodile. The crocodile is technically called Sarcosuchus. That's an adult Orinoco crocodile in its jaws. We had to try and reconstruct this. We actually look at recent crocodiles to understand how crocodiles scale. Could I have the second little video clip? You know, this field is just, and of course science in general is just filled with
I got a crocodile right here.
adventure. We had to find and measure
When they finally get a good look
the
at
largest
the quarry,
crocodiles living
they see that
today.
it's as long as their boat.
Set of chompers. Yeah, he's a big one.
If they can just land it, this croc will provide useful data, helping Paul in his quest to understand Sarcosuchus.
Okay, I need someone here.
Okay.
It falls to Paul to cover its eyes.
Watch out. No. One, you're going to have to get on the back legs.
Yeah, sure.
I got the back leg. You have the back leg? No, you have the front leg, my friend.
Baby.
I've got it. I got the back leg. Somebody get the front legs. These towels. Let's get this tape measure on him. Whoa. Right there. Wow. 65 centimeters. Wow. That's a big skull.
Big, but less than half the size of Super Croc's skull.
Enormous. We got a 14-foot croc. I knew it was big.
No matter what he does,
Don't get off. You don't get off. Don't worry about me.
Paul has his data, so they decide to release the animal back into the river.
Whoa. No. Don't get off. Don't get off. Get those legs off the ground.
Paul has never seen a fossil do that.
Okay, when I say 3, we move. Yeah. 1, 2, 3. Whoa.
So they were. Well, you know, the fossil record is truly amazing because it really forces you to look at living animals in a new way. We proved with those measurements that crocodiles scaled isometrically. It depended on the shape of their skull, though. So we had to actually get those measurements to be sure that we had reconstructed and could prove to the scientific world that Super Croc, in fact, is a 40-foot crocodile, probably a male. Anyway, you find other things, too. I'm going to lead an expedition to the Sahara to dig up the Africa's largest Neolithic site. We found this last year. 200 skeletons, tools, jewelry. This is a ceremonial disc, an amazing record of the colonization of the Sahara 5,000 years ago is sitting out there waiting for us to go back. So really exciting. And then work later is going to take us to Tibet. Now, we normally think of Tibet as a highland. It's really an island continent. It was a precursor to India, a messenger from Gondwana, a lost paradise of dinosaurs, isolated for millions of years. No one's found them. We know where they are, and we're going to go and get them next year. They're only between 13,000 and 14,000 feet. But if you go in the warm part of the year, it's okay. Now, I try to suture together a dinosaur evolutionary history so that we can try to understand some basic patterns of evolution. I've talked about a few of them. We really need to take that further. We need to delve into this massive anatomy that we've been compiling to understand where the changes are occurring and what this means. We can't predict necessarily what will happen in evolution, but we can learn some of the rules of the game, and that's really what we're trying to do. With regard to the biogeographic question, the Earth is dividing. These are all land-loving animals. There's a couple of choices. You get divided, and a continent's division corresponds to a fork in the evolutionary tree. Or you're crafty and you manage to escape from one to the other and erase that division. Or you're living peacefully on each side, and on one side you just go extinct and you survive on the other side and create a difference. And then the fourth thing is that you actually did one or the other of those three things, but the paleontologist never found you. And you take those four instances and you realize you have a complex problem. And so in addition to digging, I think we have some answers from the dinosaur record. I think these dinosaurs migrated, we call it dispersal, around the globe with the slightest land bridge. They did it within 2 or 3 degrees of the pole to maintain similarity between continents. But when they were divided, indeed they were divided. And we do see the continents carving differences among dinosaurs. But there's one thing that's even more important, and I think that's extinction. We have downgraded this factor. It carves up the history of life and gives us the differences that we see on the dinosaur world towards the end, right before the bolide impact. The best way to test this is to actually create a model. So if we move back, this is a 2-dimensional typical tree of life. I want to give you 3 dimensions. So you see the tree of life, but now I've added the dimension of area. So the tree of life is normally divergence over time. Now we have divergence over time, but we've created the 3rd dimension of area. This is a computer program which has 3 knobs. We can control those things that we're worried about: extinction, sampling, dispersal, going from one area to another. And ultimately, we can control the branching to mimic what we think the continents were like, and run it 1,000 times so we can estimate the parameters to answer the question whether we are on the mark or not, at least to know the barriers of the problem. So that's a little bit about the science that I do. I'm going to spend the rest of my few minutes up here talking about the other stuff that I do in Chicago, which is related to the fact that I never, and actually I'm talking to a lot of TEDsters, there's a number of you out there. I don't know that I'd get an answer honestly if I asked you to raise your hand, but the number of you out there that started your scientific, technical, entertainment career as failures by society's standards, as failures by schools. I was one of those. I was failed by my school. My school failed me, who's pointing fingers. Several teachers nearly killed me. I found myself in art. I was a total failure in school, not really headed to graduate high school. And I went on, that's my first painting on canvas. I read a dictionary. I got into college. I became an artist. Okay, I started drawing. It became abstract. I worked up a portfolio, and I was headed to New York. Sometimes I would see bones when there was a body there. Something was going on in the background. I headed to New York to a studio. I took a side trip to the American Museum, and I never recovered. But really, it's the same discipline. They're kindred disciplines. I mean, is there anything that is not visualizing what can't be seen in terms of discovering this dinosaur bone from a small piece of it that's out there, or seeing the distortion that we try to see as evolutionary distortion in one animal to another? This is a very extraordinarily visual. I give you a human face because you're experts at that. It takes us years to understand how to do that with dinosaurs. They're really kindred disciplines. But what we're trying to create in Chicago is a way to collect together those students who are least represented in our science and technology spheres. We all know, and there's been several allusions to it, that we are failing in our ability to produce enough scientists, engineers, and technicians. We've known that for a long time. We've gone through the Sputnik phase, and now as you see the increase in the pace of what we're doing, it becomes even more prominent. Where are all these people going to come from? And a more general question for our society is, what's going to happen to all the rest that are left behind? What are all the kids like me that were in school, kids like some of you out there that were in school and didn't get a chance and will never get a chance to participate in science and technology? Those are the questions I ask. When we talk about Ethiopia, and it's very important, Niger is equally important, and I'm trying desperately to do something in Niger. They have an AIDS problem. The U.S. State Department asked the government recently, what do you want to do? They gave them 2 problems. Dinosaurs was one of them. Give us a museum of dinosaurs, and we will attract tourists, which is their number 2 industry. And I hope to God the United States government, me or Ted or somebody, helps us do that, because that would be an incredible thing for their country. But when we look back at our own country, we look back at our cities, the cities where most of you come from, certainly the city I come from, there's just legions of kids out there like these. And the question is, and we started to address this question for centuries, as to how we get these kids involved in science. We've started in Chicago an organization, a nonprofit organization called Project Exploration. These are 2 kids from Project Exploration. We met them in their early stages in high school. They were failing to poor students, and they are now one at the University of Chicago, another in Illinois. We've got students at Harvard. We're 6 years old, and we created a track record, because when you go out there as a scholar and you try to find out longitudinal studies, track records like that, there essentially are very few, if none. So we've created an incredible track record of 100% graduation, 90% going to college, many first generation, 90% of those choosing science as a career. It's an impressive track record, and so we look back and we say, well, we didn't really exactly work this out theoretically from the start, but we look back, there are theoretical movements in science education. It's gone through science as an inquiry, which was a big advance, and Dewey back at Chicago, you learn by doing, to you learn by envisioning yourself as a scientist. And then you learn to envision yourself as a scientist. The next step is to learn the capability to make yourself a scientist. You have to have those steps. It's easy to get kids interested in science. It's hard to get them to envision themselves as a scientist, which involves standing up in front of people like we're doing here at this symposium and presenting something as a knowledgeable person, and then seeing yourself in the role as a scientist and giving yourself the tools to pursue that. And so that's what we're going to do. We're planning a permanent home in Chicago. We have lots of ideas, but I guarantee you this one thing, and I've talked to some people here at TED, it's not going to look like anything you've seen before. It's going to be part school, part museum hall, part conservatory, part zoo, and part of an answer to the problem of how you interest kids in science. Thank you very much.